Hi, it's Glenn, and I'm here with the Thermochemistry and Biology Virtual Lab. I have saved this under a different name on my computer after downloading it in order to be able to edit the file. And I'm about to get a beaker, and I can get them from here. And then I'm going to add some 0.3 molar ATP solution. Okay. There is something peculiar about this lab that was not in the instructions. The lab asks you to find the total liquid mass, but the only way to do that is to use a scale. There's a scale. So you can't use the scale with more than one beaker at a time. You have to weigh this beaker, and then you can press the tare button, or you can write down this mass. You know what I mean? And then you have to let me do both. So you can use the tare button to make the scale think that this beaker is 0. That means whatever goes into the beaker will be weighed by the scale. Okay. And then you can add your ATP solution. Let me try 33.3 milliliters. Okay. And then you'll be able to use the scale on this. Now, the reason why this is a little weird is because you cannot do the same thing with other beakers. Like once I have, to make this simple, each empty beaker in this lab, strangely enough, weighs a different amount. Look, this empty beaker, it is not 0. It should have been 0 because the balance thing is tared to think that this empty beaker, when this was empty, it was 0. And look at this. There's yet another number here. So all of these beakers weigh some random different mass. So before you put your solution into your beaker, you need to weigh your empty beaker and either write down the mass so that you can subtract the empty beaker mass from the full beaker mass, or press the tare button with your empty beaker on the scale. Okay. Right now, there's one other thing here that's a little weird. Watch this. I take the enzyme solution, which is my next step. So, how much did I add? I added 33.3 milliliters of solution. What was the temperature? Let me just check that. It's 25.0 degrees Celsius. And I'm going to add some enzyme solution. Now, when I add the enzyme solution, I'm going to watch this temperature. Okay, watch that. I'm just going to add 1.1 milliliters. Watch that temperature. Watch that. 26.45. Did you see that? It was 26.45 degrees Celsius, and it is dropping really fast. It's dropping because this beaker is cooling off because the room was 25 degrees Celsius. So that's a little difficult to see the new temperature in the beaker, 26.45 degrees Celsius. This question, what is the new temperature of the beaker? I'm looking for the highest temperature. So you would have to look at that really, really fast. I added 1.1 milliliters of enzyme solution. Now there's a way around that. If I just get, all right, so, but I will show you that way after I weigh the beaker. So now I'm going to put this full beaker on the balance, and I get 40.8671 grams. So total liquid mass is 40.8671 grams. Now you notice that I put the beaker on there and it says 40.8671. It doesn't say 200 something. That's because I tared the beaker with the empty, I tared the scale with the empty beaker on the scale. Meaning the scale thinks that the empty beaker weighs 0. So whatever is in the beaker is what's getting measured. Okay? Okay. Now for the problem of that temperature. So what is a good way to prevent the beaker from cooling off so quickly? You see it's almost at 25 now. There is a way to do this, and I'll show you now. You get your empty beaker. You get the mass of the empty beaker, or you tare the scale to the beaker. You add your ATP solution, and then you right-click on the beaker. This is a step that's not in the instructions, and it's not required. It's just a hint to make your lab a little easier to do. Right-click on the beaker, select Thermal Properties, and then select Insulated from Surroundings. Click on OK. So now the beaker will not change temperature by cooling off to the room's temperature. Watch as I add this 1.1 milliliters just like last time, 26.45 just like last time. However, the beaker stays at 26.45. So that extra step, right-clicking and then that extra step, right-clicking and doing thermal properties and making sure that insulated from the surrounding is checked, that is what is responsible for making this temperature stay high. Do not set the temperature to anything, however. If you set the temperature to something, you're not going to get the change in temperature due to the enzyme, as you should. So that's it. That's the hint. So those are the two weird things about this lab. The use of the scale. Each scale has to have its own beaker, and then the use of the thermal isolation, thermal properties, insulate. All right. So, anyways, I can continue now. What was the temperature change? The temperature change was this minus that. It's 1.45 degrees Celsius, and I'm fine if you write such an answer, but I would prefer. Without any points penalty, I would prefer 1.5 degrees Celsius, because when adding and subtracting significant figures, the answer must be only as exact as the least exact number. This number is exact to the hundredths place. This number is exact to the tenths place. Therefore, the answer should be exact only to the tenths place. All right. That is for adding and subtracting with significant figures. Now here, the heat transfer, please just use this simplified equation. Simplified equation is just Q equals MCAT. Q is the heat in joules. The mass is the M, and that was 40.8671 grams. The C is the specific heat capacity of water, because the solutions were mostly water. And the delta T was the change in temperature, which for me was 1.5 degrees Celsius. On my calculator, where is the calculator? On my calculator, that is 40.8671 times 4.184 times 1.5. It's just times, times, times all the way through. The answer is 256 joules, right? Yes. However, this only has two significant figures. So the rule in multiplication and division is the answer can only have as many significant figures as the lowest number of significant figures of all the numbers. So there are two significant figures here, 4 here, and 6 here. So I want my answer to have two significant figures, so I round this to 260. The 0 is not significant because at the end of a number, 0 is only significant if there is a dot, but there is no dot. So 260 has two significant figures. I no longer require you to keep the keep the significant figures rules, so no need to worry about that unless you intend to become a medical lab technician or a clinical laboratory scientist. How many moles of ATP were present for that reaction? So it was 0.3 moles in 1 liter. I'm going to multiply that by the liters. Now I had 33.3 milliliters here. So that really equals 0.0333 liters. I'll show you how I did that. this is 0.00333 liters. Multiply those together. Don't need a calculator for that. Maybe I do. So it's 0.3 times 0.0333. So that's 0.0999. Is that right? No, it's 0.00999 moles. Let me show you how I did that. Pencil. Decrease the size of the pencil to maybe 3. Right. All right. So 0.3 moles in 1 liter. Now, what I had was 33.3 milliliters. But there are, in 1 liter, 1,000 milliliters. So these are nicely arranged so that the liters could cancel and the milliliters can cancel. Notice that there's nothing underneath the 33.3 milliliters because that's just a piece of data from my own experiment. It is not a conversion factor or some measurement like moles per liter, with 2 different units. It's just a single piece of data. So I do that on my calculator, and it looks like 0.3 times 33.3 divided by 1,000, and that's 0.00999. 0.00999, and that's in moles. Now, to keep the rules of significant figures, this information only has one significant figure because zeros at the beginning are never significant. That means this must also have only one significant figure. To round this to one significant figure, this 9 gets bumped up 1 because this number is more than 5. So that's going to make it a 10. There. This is a 10, except this 0 is not significant. So it's just 0.01 moles. That's my answer with one significant figure. So it's really just 0.01 moles for me. Again, I don't mind if you don't respect the rules of significant figures. Divide your Q over the moles. Okay, I could do that. My Q was 260 joules. My moles were 0.01 moles. And so the answer is 260 joules per mole. That's 26,000 joules per mole. That's a lot. I'm going to do this again with a different volume. Save this file just in case. I'll do this again. Maybe I'll even do this with a different concentration, just for fun. 0.1 molar ATP, and get a new beaker, tare that new beaker, or write down its mass for subtraction later. I prefer to tare. And then I can add, I'll add 55.5 milliliters, how about that, of this 0.1 molar ATP. And now, just to make this easier on myself, I'm going to set the thermal properties to insulated. And now I'm going to add that same enzyme, 1.1 milliliters. You can add whatever amount of enzyme you want. And boom, there it is, 25.49. I'm going to take the mass of this. What is that? 60.1928. So it was 25.49. The solution, the initial temperature, oh sorry, the high temperature was 25.49. The solution concentration was 0.1 moles per liter. Solution volume that I used, 55.5 milliliters, which is the same as 0.0555 liters. Initial temperature, 25 degrees Celsius. Enzyme solution volume, just as always, I chose to use 1.1 milliliters. You can choose whatever you prefer. Temperature change, it's really 0.49 degrees Celsius, but I'm using significant figures rules, and you don't have to, but I like to, so I put 0.5 degrees Celsius. Total liquid mass, I already forgot. 60.1928. 60.1928 on the scale. The Q. Now Q equals MC delta T. And the mass was 60.1928. The C was 1.184. It's the same C, it's just for water. Delta T was 0.5 degrees Celsius. And that 0.5, that's one significant figure. So 60.1928 times 4.184 times 0.5. So that's going to be 100. It looks like 126 joules, but it's really 100 because I only used one significant figure there. If you put something like 126, I don't mind. I just want to show you how it's done right. Just because this is a chemistry lab course, even though you are probably going to be nurses, I think. By the way, about that, if you're going to be a doctor, would you please send me an email? There's something that you need to know about chemistry courses if you're going to be a doctor. But if you're going to be a nurse, I think we're fine in here. So, molar reaction enthalpy. What is this? This is joules per mole. So, just like last time, I'm going to divide my joules divided by the moles, which with the joules were 100 joules, and the moles were, what were the moles? Oh, forgot to ask you what the moles are. So it's 0.1 moles per liter. Just like last time, I'm going to multiply this by the liters. I use 0.0555 liters. So that is 0.1 times 0.0555. And that's 0.0555. Except that's only one significant figure right there. So I'll call it 0.06. 0.06 moles. 100 divided by 0.06 moles, and that equals 2,000. To one significant figure, this is 2,000 because this last number here, this first number here rounds up to a 2 because this 6 is more than 5. 2,000 joules per mole. That's a lot, especially considering that this was 26,000. It should be the same number of joules per mole. So I may have done something wrong. Let's do this on the calculator. 100 divided by 0.06. Again, 100 divided by 0.06. Yep, it is 2,000. So this should have been something like 20,000 or 26,000. Unless that was wrong. Let's see. 260 divided by 0.01. Let me try that. 260 divided by 0.01. That is 26,000. Huh. And here, 100 divided by 0.06. That is 2,000. Huh. Okay. It looks like the molar reaction enthalpy is different for the two different solutions of ATP. I don't think it should be so. Oh, I see. There's a problem right here. This is the problem right there. It is not different. It is going to be the same or almost the same. Okay, 0.1 times 0.0555. Aha, it was 0.00555, which is 0.006. This number, rounded to one significant figure, is 0.006, because this 5 needs to get bumped up 1, because the number next to it is a 5. 5 and over gets bumped up 1, so it's 0.006. Not 0.06, it's 0.006 moles. So that means this is 100 joules divided by 0.006 moles. And 100 divided by 0.006 is 16,666, which, if I round to one significant figure, is 20,000. 20,000 joules per mole. Oh, and this number, if I round this to one significant figure, this 2 is going to be a 3. So this is going to be 30,000 joules per mole. Okay, so 20,000 and 30,000. They're in the same 10,000s ballpark, right? So the molar reaction enthalpy for here and for here, in number 4, they are close enough to be considered the same, given we were only working with one significant figure in this lab. You are probably going to have numbers that work a little more closely, because if you don't choose to respect significant figures, I think you'll end up with numbers that are a little closer together than my numbers. People who designed this virtual lab may have designed it assuming that people wouldn't be respecting significant figures. I'm not sure why they would do that, though. So, now how many milliliters of the 0.3 molar ATP solution would I need? Now, to figure this out, I'm going to have to know how many joules it takes to do this task. Keep the flashlight on for 1 minute. Once I know the joules, I can figure out how many milliliters of the, I can figure out how many moles of ATP I'm going to need, and once I know that, I can figure out how many milliliters of the 0.3 molar ATP solution I need. All right? So, first of all, let me get the average of these two molar reaction enthalpies, joules per mole. So one is 20,000 and one is 30,000. The average is going to be the number in between those two, which is 25,000. So that is just going to be 30,000 if I'm using one significant figure. So I'll just stick with 30,000. So I'm going to get the board out here. Here we are with the board. It takes about 20 joules of energy. So I'm going to need 20 joules of energy. And what I want to find out is how many milliliters of 0.3 molar ATP solution. So first I need to find moles. So I got, for 20 joules of energy, how many moles of ATP do I need? Well, I know that for 1 mole of ATP, I get 30,000 joules, right? Because my average between 20,000 and 30,000, I figured out was 25,000, and I rounded out to 30,000. So this is joules of energy per mole of ATP, because I divided the joules that I got in the experiments divided by the moles of ATP that I used. So take this number, get rid of the joules by multiplying 20 joules, and then I get my answer. Divided by 30,000, it's 0.0007. So I'm going to round that to 0.0007 moles of ATP. Now 0.0007 moles of ATP. How many milliliters is that if it's a 0.3 molar solution? See, it's a 0.3 molar solution. So how many milliliters would that be? Well, if it's 0.3 moles in 1 liter, then I can just start this problem out by writing 1 liter over 0.3 moles. Why would I want to start it with 1 liter on top and 0.3 on the bottom? It's because the answer that I want is in milliliters, which is a form of liters. So I can put 1 liter down here and 1,000 milliliters up here, because 1 liter is 1,000 milliliters. This is like multiplying the whole thing by 1. Now I have milliliters over moles, but I don't want moles, I just want milliliters. So I'm going to multiply by the number of moles that I just calculated, 0.0007 moles. of ATP. And this was 0.3 moles of ATP. So I get my answer, which is 0.0007 over 0.3 times 1,000. Whoops, didn't mean to do that, sorry. There's 1,000 times 0.0007 divided by 0.3, and that equals 2. That equals 2 milliliters. Oh, sorry. So that's going to equal, all right, that equals 2 milliliters. So 2 milliliters. 2 milliliters. Oh, what about for 1 hour? Well, that here, this 2 milliliters, that was for 20 joules. And 20 joules was for 1 minute. So for 1 hour, I'm going to need 60 minutes. So I'm going to need 60 times that. 60 times 20 is 120. Of course, you can put something like 120, but I'm going to put just 100 because I'm doing this in significant figures. And 120 rounded to one significant figure is just 100. So there it is. That's the lab. There were 2 tricks, just to review, there were 2 tricks to this lab. And the first trick was you needed to use the balance with your empty beaker before you add your solution to the beaker. And the second trick was you had to look at that temperature real fast when you added the enzyme. Or you could have just right-clicked your beaker and clicked on thermal properties and checked the box insulate. Thank you. Sorry about those little 2 complications.